in general, when we find line integrals, the value of the integral is going to be path dependent, but there are circumstances where the value of the integral is not path dependent, and one of those you'll see is the electrostatic field. So we'll go and have a little look at that in general, and well, look at that in particular with electrostatic field, then look at it in general. So we had this equation here, Gauss's law for the electrostatic field. So we've got it drawn out here. So we've got our x, y, z coordinates. We have a point here, Q, so that's one charge Q, and there's our charge Q naught. So this equation here gives us the charge experienced by Q due to the charge Q naught. Okay, so this force is going to be 1 upon 4 pi epsilon naught times the product of the charges Q, Q naught, and divided by the distance between them squared. So that's the distance there between them squared, distance r, and it's in a direction given by the u hat. Okay, so that's a component, a unit component, and that is in the direction between these two charges. Okay, so it's going to point out in that direction. So what we can do is we can write first of all that our unit component u is going to be the length of, it's going to be r divided by the length of r there. Okay, so the value of r, well, you can write r simply as a vector, so you can write that simply as ix plus jy plus kz, so that's just some vector giving us that position there, and if we divide it by that length of r, we'll get this value here, which is our u hat. So then we can say that our value of our force F in the direction experienced by Q is going to be our Q naught 4 pi epsilon naught, and you can see then that this value u hat is then replaced by this value here. Okay, so we end up with this extra term on the top line, and we end up with an extra r on the bottom line, so that r now squared now becomes our r cubed. Okay, so if we were to look at this here, and we're looking at the force, and we're looking at the dot product with the tangential component, so it's the tangential component of this force times some element ds. Well, I could just put it in as our q naught upon 4 pi epsilon naught, and you can see here that if you were to take this value here for our force, you'll see that we've got I, j, and our k. So we dot product that with the tangential component. Well, I know the tangential component's got a component in I dx by ds plus j dy ds plus k dz by ds. So it means that when you look at the I component, well, the I component will multiply that I component there, which will give us 1. So we'll just be left with our x, and the ds's will cancel out. So we just have x ds, and the same thing will happen for our y, and we'll have our j y dy, and the same thing will happen for our z. The k's will multiply, and we'll have our z dz, and the other factors will disappear because our I dot j 0 and I dot k 0, and the j dot k 0 and the j dot I 0, and the k dot j 0 and the k dot I is equal to 0. Okay, so we'll just be left with this equation here. So if you're unsure of that little section there, look at the previous video where I derive this f dot t, okay, and you'll see where that comes from. So what we can note here, and a little trick there that employed really, is that we can see that that distance r is going to be x squared plus y squared plus z squared to the power of a half. Okay, so that's just this distance here. Then we can, if we were to, we can look at the differential form of this, so we can just differentiate this with respect to our r and our x, our y, and our z. It's going to give us our implicit differentiation will give us our 2r dr equals 2x dx plus 2y dy plus 2z dz, and you can divide out through the y2's, and you're just going to be left with the r dr equals x dx plus y dy plus z dz. Okay, so we can say then that this f dot tds is going to equal, it's going to be q naught upon 4 pi epsilon naught, and what we're going to do is we're going to stick this r dr in for this section here up in this equation. So we replace this here with the r dr. So one of the r's is going to cancel out and just be left with 1 upon r squared in the bottom. So you're left with this equation here. Now what we're going to do is, if we were to take 2 points, say in a curve, so we start off at point 1 and then we've got another point 2 here. And if we were to do this integral along this curve here, then what we would be doing, we'd be integrating this here from R1. Okay, so if this here, that point there, let's say that's the origin of our axis system, so we would be integrating that from R1, that's that point, to R2, which is that point P2 up there, of 1 upon r squared by dr. So when we integrate that there, we'll get our q naught upon 4 pi epsilon naught, and we'll have 1 upon r2 minus 1 upon r1. Now, the thing to note here is that this final answer here, well, this answer here is going to be path independent, so there's no path dependence within this here. So we could have went round any path in order to get to these points R1 and R2. So the value of this integral is only going to be dependent on these points R1 and R2. So you can see that if we went any direction along here and we took any other path, we would still get the same value for this integral, because nowhere in here does it mention anything about the path. It only gives you the value dependent on the points here, the point R1 and the point R2. So let's continue on. Almost finished. So that type of force there we looked at, it's called a central force. Okay, so a central force is one, it's only dependent on the distance between the points, and the force acts along the lines joining the points. So we know that there is what happens in terms of the Gauss's law. Okay, so Gauss's law satisfies both of these. So that's a central force, and central force are going to be path independent. So we could rewrite our equation there, and we'll replace our general field F with the electrostatic field E. So we can say that the integral around a closed path of the normal component of the electric field around that path is going to be path independent. So it means that we could draw out, say, 2 points P1, P2. We can draw 2 paths, that's path C1 and that's path C2. And we can say that, well, the value of line integral is the same in that path as that path. So we can write the integral of C1 of f dot t is going to be the integral of C2 of f dot t. So it means, using just basic calculus, if we were to change the direction of C1, so the path now pointed from P2 to P1, then we could say the integral of, well, minus C1 just means the path. Rather than going from P1 to P2, we're going from P2 to P1. So that's going to equal, we can take that minus sign out and just leave it with C1. It's the same as minus the integral C1 of f dot t ds. So it means that we can then write the integral of the path C2 is equal to minus the integral of the path C1. So it means then that we can say, when we add both of these together, we'll have minus C1 plus C2 is going to equal 0. But it means that this minus C1 plus C2, well, all minus C1 is the path in this direction. So what we're doing is we're going along this direction here, and we're going back down that direction there to end up where we started off. So it means that what we do is, in that case there, we put this little circular sign, so that really tells us we're going round and begin at one point and ending at the same point, round in a circle. Okay, so we're going to round, we start off at one point and then we end up back at the same point. So it means that that value there, around that closed loop of the line integral is going to be equal to 0. Okay, so we can replace this f by our electrostatic field. So we can say that the electrostatic field, the E dot TdS around this closed loop is going to be equal to 0, and we call that thing here, we call it circulation. So in words, we can say the electrostatic field that's in the tangential direction around some closed curve is going to be equal to 0. Okay, now we're going to use that fact in order to help us find the electrostatic field given a random charge distribution. So first of all, what we're going to do is, rather than look at the circulation here around this closed loop C, we're going to look at the idea of circulation at a point, and we'll be introducing that in the next video when we look at the idea of curl. So I hope this was of use to you. If it was, then don't forget to subscribe, and I'll get you on the next video. Goodbye.